We're starting looking at page 216. We're picking up here. We're doing some studies with the limbic system and the hypothalamus. Most of these studies are limbic system based, but the first, and this is typically studies done by removal of portions of the limbic system. Ablation is the terminology, and that's a term that you'll see on the test as well. So surgical removal or ablation of different parts of the limbic system got us different results, obviously, and that's how we know what those parts do. And this study also suggested, due to electrical stimulation of the hypothalamus, that those two work together in a lot of these aspects, because we could create some similar symptoms by electrical stimulation of the hypothalamus, the same as removal from the limbic system. So the first one on the list is aggression. Stimulation of certain areas of the amygdala produces rage and aggression, and stimulation of particular areas of the hypothalamus can produce similar effects. So in this particular study of aggression, they didn't actually remove a part of the limbic system. They simply just electrically probed it and got similar results. And then those results literally went down to the point they could take a very docile dog and turn him into a mad dog, and they could take a mad dog and turn him into a docile dog. They can make a dog that's just sitting there completely normal and make them shiver, or they can make them start panting. I mean, it's just different, just moving it around to different parts. Number two is one of my favorites here, fear. This was actually an ablation process, so they removed part of the amygdala of the limbic system. And what they found in monkeys are so afraid of snakes, they really throw a hissy fit when there's a snake around. They're not even going to get close. So when they went in with the ablation process and removed the amygdala of the limbic system, they saw after surgery that the monkeys were playing with snakes. I mean, they're just picking up, handling them like they're just little toys. So the amygdala portion of the limbic system deals directly with fear. So once you remove that, you have no fear. And that's a direct test question, by the way, about monkeys. You know I'm going to have a monkey test question on there, right? And then feeding. The hypothalamus contains both a feeding center and a satiety center. Electrical stimulation of the former causes overeating. So if we stimulate your feeding center, you just commence to eat until you don't know when to quit. You just eat yourself into an oblivion. I think I've got a tumor in that center right now because I just eat all the time. Something's putting pressure on it, I'm telling you. The stimulation of the latter will stop feeding behavior in experimental animals. So we have a satiety center that says, oh, I'm good, I'm full. And you may not have eaten anything just by electrically stimulating that. So is the next major diet program of the world going to be an electrical probe that's surgically implanted in your brain? All you have to do is punch a little remote control button that says, I'm good. Now, some people literally starve themselves to death doing that, wouldn't they? They wouldn't know at what point, the doctor prescribed, when you start to eat a meal, you need to punch this button 3 times. They'll just sit there and hold it down, probably, because that's the only problem with things like that is, where is the control mechanism? If it's you that has control, you wouldn't have been in that the first place. You wouldn't have had to have the surgery in the first place because you could have controlled your eating mentally. So I mean, it's a catch-22. It's a great idea. Probably somebody's going to sell it one of these days, right? Who knows? And then number 4, the hypothalamus limbic system are involved in the regulation of sexual drive and sexual behavior, as shown by stimulation and ablation studies in experimental animals. So the cerebral cortex is also involved in some conscious thought when you get into higher animals when it comes to sex and reproduction. But it plays some role in smaller animals, but the higher the animal, the more thought process. And that's what they tell you in the rest of that paragraph. Number 5, goal-directed behavior, reward and punishment. Now this is where we could raise our kids with one of those electrical probes. If we can get one of the electrical probes put in the kids' heads, where we have control or remote control. And we say, little Johnny, I don't need you to do that anymore. Yes, Father. You know how respectful little Johnny is. Yes, Father. And as soon as we turn our back, he does it. And we just turn around with remote control and zap him. He goes, oh man, wish you hadn't done that. Well, I asked you not to do that. That's negative feedback. That's how our whole system works, isn't it? Negative feedback. So that those laws of, oh, don't put a hand on your child, you'll mess up their psyche. Their psyche needs some messing with. I mean, children are born already born in ways of doing evil things, but it's our job as parents to align those ways to be off of evil and back to good. How else you do it but correcting them? Now, yeah, granted, you don't need to sit around an electrical probe all the time and zap them, but look at the reward side of it. I mean, when they do something good, how often our parents, and you can look back to your own parents, how often do they really praise you for doing something good? And I'm the world's worst. I find the bad because I'm the evil one of the parents. I'm the one that has to do all the evil things to them. And so daddy's just mean. But when they really do something good and you're really proud of them, how many times do you hear, oh man, that was a great job. I wish you'd have done that more. And just, did you hear that much growing up? Not as much as we'd like to have heard, but you know the parents enjoyed it. They knew it was good, but did you hear it? Well, we can take this electrical probe and just give you some reward. And according to this, man, this reward is good. This is some good stuff. Well, the reward more powerful than food and sex in behavior studies done with rats. But when it comes to humans, it didn't replace food or sex. The reward was a feeling of ecstasy. In other words, we lowered our blood pressure. It's still pretty good though. Is that not a relaxing feeling to, man, that's good. So that's electrode placed in different positions apparently stimulate punishment. And if we could have 2 electrodes and 2 buttons, boy, we could manipulate a child. We could just, and next thing you know, that's still the remote, right? And you'd see little Johnny sitting over in the corner hitting that reward button. Zzz, zzz, he's getting high off the reward button. That's what would happen. Of course, as parents, we'd lose the remote somewhere and wouldn't be able to find it to punish the kids. So, but in animals, in experimental animals, when they hit that punishment button, they stopped what they was doing. So it worked. It worked in animals. If they was headed the wrong direction in a maze, zzz, they'd go a different direction. They'd do something different because that wasn't working. So it's a thought. It's never going to happen in children, but who knows? Maybe you can develop that, be the next behavioralist, put it that way.
My luck, I'd get sued.
I'm not going to say Dr. Spock because he probably screwed up human behavior more than any psychologist ever out there in today's time. But yeah, you'd have to have a massive insurance policy to take over you.
That would require testing on children.
Yes, it would. But those are some neat studies to read back through and get a little grip on. I love these studies that they do human-animal comparisons to, because they don't always work out the same. This rat, boy, I mean, liked it. It was the greatest thing, better than food or sex. It doesn't get any better than food or sex for a lot of animals. When it comes to humans, it just lowers our blood pressure and relaxes us. Well, sometimes that's really good, because how often do we get to sit back, relax, and lower your blood pressure? Not very often anymore. It's a high-stress society, isn't it? So this could be actually a longevity thing for life. If you just come home every day and hit the reward button and sit back in the old lazy boy and relax for a few minutes. Well, let's look at brain regions and memory. Your bottom line in memory is we have short-term and long-term, and we attempt to lay down long-term memory, and especially we'd like to in a class like this, because we know somewhere down the line in the fields we're going to have to use this stuff at some point. But it's easier said than done. So we tend to survive off the night before study, crash cram for the test. We cruise in here, we're still studying till the point I lay the test on your desk and you finally close the book. And you work off that short-term memory and you finally get finished with the test, and some of y'all can knock out an 80-question test in 20 minutes. That's 30 seconds. That's 30 seconds. That's 20 seconds, isn't it? 20 seconds a question. Boy, you worked that short memory. As soon as you walked out that door, how much do you remember? If they hand you the test again, would you do as well on it? I mean, if it took too much, 2 or 3 days later, would you do as well on it?
No.
Probably not. Probably not. Where you really start learning, where I started learning more and more physiology, was up here teaching it for 20 years. Where you really start learning, it's when you start applying it in your field, and you understand application in your field. The lab's purpose is to attempt to apply, but they're not gonna give us probes and electricity to do our own research. We're not qualified, so we live off other people's research, and we look at sheep brains, and we look at whatever we can, and different lobes, and see what's happening in different lobes, and these are all dead brains, so we can't kill them again, and that's a safety precaution, I'm sure, to keep us from destroying something else. Short-term and long-term memory. They've done some electroconvulsive shock therapy, and I hope nobody in here ever has to go through that. But people with head trauma and patients who undergo electroconvulsive shock therapy may lose their memory of recent events but retain older memories. You see that a lot in the elderly. They can recall events from their childhood, but they can't remember where they put the car keys. And as my grandpa was getting older, Lord, he'd tell stories from years ago. He told stories of when he was in that single room schoolhouse and how pretty his teacher was. And he's just like a fifth grader, you know. I'm not sure they'd list them as fifth graders, because they'd be all different ages in one schoolroom back in those days, and you'd have them ready to graduate to start all in the same room, one teacher. But he could recall those memories and not remember what happened yesterday. So it's going to happen to all of us at some point. So that's kind of an old age thing too, but electroconvulsive shock therapy does that as well. The conversion of short-term memory into a more stable long-term memory is called memory consolidation. We do that by spending a lot of time with whatever the topic is. The more we repeat it, the more we read it, the more we're around it, the more you like it, will help lay down long-term memory. So long-term memory is classified as non-declarative or implicit memory, and declarative or explicit memory. Non-declarative memory refers to the memory of simple skills and conditioning, such as remembering how to tie shoelaces. Well, my 6-year-old just learned how to tie her shoelaces. I think her teacher told her she wasn't going to pass her the next grade because this is a lazy thing. And my oldest son was the same way. Nick wanted Velcro shoes so he didn't have to tie shoelaces. But when the teacher threatened not to pass him next grade, that really hurt his psyche. And so we learned how to tie shoes. So now you can use these little manipulations on your kids. We use my kids as the experiment. So it tends to work. My 6-year-old just learned non-declarative memory. The declarative memory is memory that can be verbalized. It is subdivided into semantic and episodic memory. Semantic memory would remember the names of bones. Now 20 years on down the line, you still going to remember some bones that you learned in anatomy? Sure, you're going to remember some of them. Will you get every little intricate bone in the hand and feet? Those weren't that important, were they? But that big femur and the radius and the ulna, and I mean, those things come into play, don't they? The calcaneus. See, I hadn't taught anatomy forever, and I can sit here and rattle some of them off. And so those kind of things are going to stick with you. Then episodic memory would be remembering the experience of taking a practical exam on the skeletal system. Oh, I'm sure you have memories of how terrible that exam was. Sometimes even nightmares, just like the old Zoe test yesterday, right, Amber?
Yeah.
You aced it nearly, didn't you?
Yeah.
Did well. I was real proud of both classes. That was my hardest test in Zoe. You remember test 3 in Zoe?
Yeah.
Those classes, I guess I scared the weebie-jeebies out of them because they really studied on this one. And they did well. Well, the medial temporal lobe consolidates a lot of long-term declarative memory, and it utilizes the hippocampus and the amygdala to do it. Hippocampus and amygdala that's found in the medial temporal lobe plays a huge role, and I'll have a test question about the hippocampus playing a role in long-term memory. They tell a little story here on a guy named H.M. H.M. had epilepsy. They went in and surgically removed part of his brain that they felt like was causing epileptic seizures. And in fact, they removed the right and left medial temporal lobes. Surgical removal of the right and left temporal or medial temporal lobes. After surgery, he was unable to consolidate any short-term memory. He could repeat a phone number and carry out a normal conversation, but he could not remember the phone number if momentarily distracted. I have that problem now. None of us remember phone numbers anymore. Why? Because they're in our phone, right? Yeah. we've created a lazy society, but one that doesn't have to utilize the brain as much. I mean, when I took math in high school, calculators weren't allowed. They wanted us to use our brain. Have math races on the board just to utilize speed of the brain functioning. And now I'm sitting around and I'm always miscalculating my brain because I've created a lazy brain because, well, let me get my calculator. Where's our calculator? In our phone. So where's society going? We've got the world at our fingertips. So in a way it's good, but in a way we've got Bill, what if you lost your phone? We wouldn't know what direction to go. Where's our compass? In that phone. We're going to be lost in the world. We rely on that thing so much. So HM was in the declarative memory, and his non-declarative memory, perceptual motor skills such as how to drive a car, was still intact. So what say a friend come in his room after surgery, he would not know that friend. And the friend would introduce himself to him. Hey, Jim, I'm your neighbor. I've been taking care of your livestock while you've been in the hospital. And how's things going? Jim said, well, I don't really know you, but things are going well, and I appreciate what you're doing for me. Both of them understanding what this surgery did. And they talked for 10 minutes, 15 minutes, and the nurse comes in to do something and asks the friend to step out. He's out for 5 or 6 minutes and comes back in. HM had no recollection his ever in there to start with, so we start this conversation over again. What is that movie, 100 Dates or
Yeah,
50 First Dates? 100 Dates, who remembers, right? Had the same thing going on. So on the basis of additional clinical experience, it appears that the hippocampus is a critical component in the memory system, and for consolidation of short-term and the long-term, which is stored in the cerebral cortex. And they believe that sleep plays a huge role in storing long-term memory as well, and not so much REM. They think REM may help, but they want you to get into that deep sleep where there's no other conscious activities going. The limbic system's kind of stalled out, and it's not actively working, and we can lay down some long-term memories from that. So REM is needed for optimal memory consolidation by the hippocampus, but as you read on, they'll think there's a place that REM is used, but when you get into the deeper sleep, that's when your memory's getting the relaxation that it needs to do better. Let's see. Acting by way of structure of the limbic system, we can enhance or inhibit long-term memory storage. For example, stress has been shown to produce deficits in hippocampus dependent learning and memory. Well, we already identified stress as a lot of different things, but if stress is bothering you enough, a lot of times it'll inhibit sleep, won't it? So if you inhibit sleep, you're going to inhibit your ability to remember things. If you're in stressful times, and you ever been stressed out to the point you missed an appointment, or you forgot to do something, or something you're supposed to do, you forgot to pay a bill, and you just had so much on your mind, well, this is what it's talking about. I mean, you don't get an opportunity. What really inhibits memory here is the corticosteroids that's produced in high levels of stress, which will also lower your immune system. So they're telling you that in here as well. The left inferior frontal lobe, they've identified it to be very good at performing exact mathematical calculations. Well, you want to use that one if you want to be precise and exact, right? I'm not sure which one kind of gets close, but this one's exact. See what I'm saying? A lot of us get close, but this one's exact. Amygdala deals with fear. Then your working memory. Working memory is actually the ability to remember a number or remember something long enough to write it down or tell somebody or something like that. And that's I mean, we use that quite a bit. You may be able to store something in your mind long enough to go get it done. Me, I try to remember it long enough to write it down, and then I look back anyway to make sure, because I'll talk myself out of it. Clinical application, there's Alzheimer's. For reasons not fully understood, people with particular allele of a gene of a apolipoprotein E are 3 to 4 times more likely to develop Alzheimer's disease between the ages of 60 and 70. So I'm sure they can test for this. I'm not sure you want to know. That's the key. So this increases your chances of having a particular allele that they've linked to Alzheimer's fixing it, well, we don't have a fix for it, obviously. But at least we know more about it now than we did yesterday. Clinical observations support the notion that the intellectually rich and physically active lifestyles may offer some protection against Alzheimer's, perhaps by building up a cognitive reserve. There's also evidence that eating a diet restricted in calories and saturated fats and enriched in vitamin C, E, and folate may afford some protection. Listen to Paul Harvey before he passed away. Anybody ever listen to Paul Harvey? You know who Paul Harvey is? I always found his shows, the rest of the stories real informative and keep your curiosity up. But I don't remember exactly what the story was, but I remember him saying on there one morning that when people retire, if they don't have some activity to remain active, at least in the brain, they need to take up reading, or they need to remain active. They can't just retire physically and retire mentally at the same time. Now, literally, one of the studies said, and I love the way he put this, one of the studies said that your brain cells, if they're not remaining active even after retirement, they will actually start committing suicide. And that's basically what they're talking about here. If you remain physically active, which is going to keep blood supply going to the brain, would you agree? And mentally active, keeping yourself alert, getting proper rest, even after you retire from this job, go do something else you enjoy, then you're more apt to live longer and reduce the chances of Alzheimer's. Now, reducing the chances and absolutely reducing the chances, I know some people that retired and they got Alzheimer's anyway and they were pretty active. So sometimes the genes may overcome, or maybe they weren't as active as they needed to be. I don't know. But these were some highly intellectual type people that I don't know what happened. But we've heard about the vitamin C's and E's and folates and things like that. So, I mean, we need to maintain good, proper levels of that. Grapes is a great one to eat. It has a lot of the good stuff in it. So if you like grapes and grape juice, then that's good for you. Synaptic changes in memory. This is because long-term memory is not destroyed by electroconvulsive shock, it seems reasonable to conclude that the consolidation of memory depends on relatively permanent changes in chemical structure of neurons and their synapses. So we said back earlier in long-term potentiation, which the next paragraph is talking about, that if it's something you like, your brain's going to produce neurotransmitters that's going to lay down that memory. If something you're lacking interest in, then it's like it can't pique your interest enough to even fire off neurotransmitters. It's like a bad meeting you have to go to, and they force you to go to them all the time out here. It's like, when's this going to be over with? What'd they say? Who cares? You know. And we've all had classes like that. So, this thing gonna last a whole semester. It's hard to stay focused in some of these classes. So the neurotransmitter is extremely important. And sometimes things you have to learn, you read it 3 times and say, what did I just read? Because your mind's somewhere else where your interest is. Then you really have to concentrate and focus on that to get it in your mind, to start firing synapses, and it's just more difficult to do. Long-term potentiation has been studied extensively in the hippocampus, where most of the axons use glutamate as the neurotransmitter. So once we get glutamate firing off, you've got a greater chance to lay down long-term memory. Emotion and memory, the limbic system on 221. Of course, we've already mentioned the fact that emotion can play a role in memory. Stress plays a role in memory. And it's crazy how emotions really play a role in memory. Some emotions, sometimes, well, let's put it this way. Some great emotions, some of the happiest times of your life, you'll never forget them. And then some of those emotions that you'd like to forget, think whatever traumatic event that occurred, you'd like to forget, you may never forget it, and then some people block them out totally. So everybody functions a little different in this aspect, but emotions can play a role in whether you remember this event or not. And we tend, I don't know why that is, we tend to have it stuck in our mind, those things we'd rather not. And then the things we'd rather remember details about, they seem to be more vague. I think we're so high on adrenaline at the time, adrenaline wasn't the neurotransmitter we needed, I guess. Emotions enhance memory encoding with the amygdala, but stress can impair memory consolidation by the hippocampus and the cognitive functions and working memory performed by the prefrontal cortex. So demonstrations that people with post-traumatic stress disorder often have hippocampal atrophy. So their even long-term ability down the road is going to be decreased by atrophy of the hippocampus. During stress, there's an increased secretion of stress hormones, what I was mentioning a while ago, and that the hippocampus and amygdala are rich in receptors for these hormones. The hippocampus and amygdala are thus targets of these hormones, and corticosteroids have been shown to suppress neurogenesis in the hippocampus. So stress inhibits memory. You ever heard of test anxiety? It's exactly what that is. I say test, they go into stress. They go into stress, corticosteroids go up, and they just can't remember it because they're stressed for the test. Now, the best thing they could do is just relax and not worry so much about it. A former instructor of mine told us one time, he said, and this is even in some of the books he was using told us that stress really didn't affect society a whole lot, but these were ancient books, but he already knew it did. And his statement was, you really shouldn't sweat the small stuff. That's the term he used. Don't sweat the small stuff. Then he finished it by saying everything is small stuff. If you look at it like that, then what are you worried about? Well, test is just a small hoop in life. If they stress over a test, oh my gosh, what's the rest of life going to do to them? Because it's brutal out there. Some of y'all have already seen brutality in society, but it's pretty brutal. Prefrontal cortex. Orbital frontal area of the prefrontal cortex seems to confer the ability to consciously experience pleasure and reward. And this is supposedly in the prefrontal cortex. With that, it receives input from all the sensory modalities such as taste, smell, vision, sound, touch, and others, and has connections with many regions of the limbic system. Connection between the orbital frontal cortex and the amygdala and the cingulate gyrus are notably important for the emotional reward of goal-directed behavior. People with damage to the lateral prefrontal area of the precentral cortex show lack of motivation and sexual desire, and they have deficient cognitive functions. People with damage to the orbital frontal area of the prefrontal cortex, in contrast, have their memory and cognitive function largely spared by experience, but experience severe impulsive behavior verging on sociopathic. And then they talk about Gage, the railroad worker. Did we talk about Gage the other day? We didn't mention Gage in here. I did the other class because it kind of fits back when we're talking about the different lobes. To just give you an idea of what the Gage, the railroad worker here is. This is a story, and you tell me what lobe or lobes may be affected here, but Gage was a railroad worker back in the day that heavy equipment wasn't really heard of. He had a team of horses and some dynamite and some matches and gunpowder, and that's how he did his job. And his job was to remove large obstacles out of the way, whether it be a tree or a boulder, out of the way for them laying down the rail. Okay? So he stayed ahead of the main railroad workers and kind of worked alone with a team. If he's going to move a big boulder, in today's time, we'd just move the big boulder. Back then, you had to make it into little boulders. So he had to blow them up. So that's what he was doing one day. He had created a crevice inside of this boulder where he felt like he could get enough pressure in there to start cracking or blow up this boulder. And so he poured some gunpowder in there, and he was tamping it in real good to get a good explosion. And as he was tamping this gunpowder, he was using a 3-foot steel pole to tamp it with. He wasn't quite careful enough, and he threw a spark into the gunpowder, and it exploded in his face. Well, it exploded to the extent that it shoved that 3-foot steel pole up through here, right up through top of his head. And they didn't, maybe they said, I don't remember how far it blew him away from the scene. Probably should have killed him, but it didn't. And there's Gage laying out there in the middle of nowhere, big explosion. Everybody's used to explosions, so they didn't think anything happened, but there he was laying out there. And when it knocked him out, they didn't say how long, but when he come to, he had a lot on his mind. I always had that, kind of make my own story out of this. But believe it or not, can you imagine the headache this guy had? And he got on his horse. His horse didn't run off. He got on his horse and he rode into the nearest town, which no telling how far that was. And went to the doctor at the nearest town. And the doctor at the nearest town, knowing him, When you come to the door, I can see it, Gage knocks on the door, doctors open up, says, Gage, what's on your mind today? Obviously a 3-foot steel pole. You won't find that in any book either, I made that up. So they go on with the story. See what you'd have missed if you hadn't come today? They go on with the story saying they surgically removed this 3-foot steel pole and Gage survived. Gage lived, and I don't think he saw very well because it took out part of his left eye. But then at that point, Gage, he may or may not show up to work. He's never, before, he took care of things. He didn't drink, he didn't cuss, he took care of his family. Now he didn't remember if he had a family half the time or not. He cussed like a sailor, he gambled, he drank, he didn't do any of that before. Eventually got fired from his job because he may or may not show up. He may not even remember he had a job. So what part of his brain was damaged? What lobe? It's a frontal lobe, going right through the left eye, right up through it, hammer that front. Changed his total personality, didn't it? And he wasn't even the same person, and that's really the whole concept of the story. Gage was no longer Gage after this accident. Have you ever known anybody go through an accident and totally change them like that? Oh, I've seen them. And not near as traumatic as that accident, I've seen them. So, yeah, that's the stage of Gage. That's the story of Gage, the railroad worker, and kind of what happened. So, no longer Gage is where he was at. On 222, the thalamus and epithalamus, here's what you need to know about the epithalamus. This is where your cerebral spinal fluid is made. Your cerebral spinal fluid is made there. Then the hypothalamus and pituitary gland, we know that they work together for a lot of things, just like the hypothalamus works with the limbic system with a lot of things. They simply list here that located below the thalamus, the hypothalamus forms the floor and part of the lateral walls of the third ventricle. This small but extremely important brain region contains neural centers for hunger, thirst, regulation of body temperature, hormone secretion from the pituitary, regulation of sleep, wakefulness, sexual arousal, performance, emotions such as anger, fear, pain, pleasure. What does it not do? It's one of those things that if it's a choice on a question, you could literally put it, and we could arguably connect it to that question somehow, some way. It's got to be connected. I mean, it's involved in nearly everything going on. We see it involved with our instinctive behaviors, the limbic system, and now out here working with the thalamus as well, and the pituitary gland. Hypothalamus helps to evoke visceral responses. That's in digestion. In various emotional states, in its regulation of emotion, and hypothalamus works together with the limbic system, and that is a great statement. And I'm glad they made that statement. They've already said it previously. And in a later part, I don't know if it's this chapter or the last part of chapter 9, it'll tell you it's part of the limbic system, but it is not. The hypothalamus is its own entity. It works closely with the limbic system, as it states right here, but it's not part of the limbic system. So I want you to clarify that. Regulation of the autonomic system, stimulation of different areas of the hypothalamus can evoke autonomic responses characteristic of aggression, sexual behavior, hunger, and satiety. Just like the research that showed us on previous pages, where we could electrically stimulate those things, and we know now that it works directly with it. And sometimes we can make an animal eat to obesity, and sometimes we can totally stop their eating. It also is where the body's thermostat's located. They can cause shivering, and some dogs will start panting just by moving the electrical probe. Coordination of sympathetic parasympathetic reflexes is thus integrated and control of somatic and endocrine responses by the hypothalamus. The activities of the hypothalamus are in turn influenced by higher brain centers. Now, the higher up you get in the animal world, the more of these centers come into play. We consciously think about things. A lot of animals don't. They live off total instinct. Regulation of pituitary gland. We know that pituitary glands producing our tropic or food hormones, and the hypothalamus helps work with that by producing, inhibiting, and promoting hormones, inhibiting and releasing hormones. Circadian rhythms. The SCN is what they call it, believed to be a major brain region involved in regulating the body's circadian rhythms, the CNN region of the brain. What this is involved in is our day-night cycles, whether we sleep well shift work messes this system up. You have to adapt back to where you're at. And this plays a huge role in serotonin production, as we talked about earlier. Since fish, amphibians, reptiles, and birds have photosensitive cells in their brain and can detect light passing through their skulls. Well, they probably need to, since they live out in society all the time. We don't necessarily need to, because we can flip lights on and off. But now, they believe we have cells that get information about light day and night in our organs. As they'll tell you, they're circadian clock genes, not only in the CNS, but found in the heart, liver, kidneys, skeletal muscle, adipose tissue, and other organs. These are genes that have circadian circles, or cycles, of activity caused by circadian cycles of histone and chromatin modifications. So the master clock is the SCN, which receives information about day-night by way of the retinal hypothalamic tract. So there's the hypothalamus involved and light coming through their eyes. So if you close your eyes, light's not coming through. If your eyes are open and light's coming through, and typically it's based off of day-night outside. We kind of mess that up by flipping lights on and off, and that's how we mess these things up. But closing your eyes helps that process stay cyclical, if you will. Let's see, midbrain. 225. This is mentioning a little bit about substantia nigra, which we know degeneration of substantia nigra is Parkinson's, and they talk about that quite a bit there. And then the mesolimbic system that projects dopaminergic input to the limbic system of the forebrain is also here. And this system is involved in behavioral reward, which we just saw hypothalamus is too. So there's the limbic system in behavioral reward, hypothalamus is in behavioral reward. And they found that abused drugs promote the release of dopamine in the nucleus accumbens of the forebrain. So, and usually when they say dopamine, it's going to be some cocaine type product that can mimic dopamine. And the immediate rewarding effects of addictive drugs appear to be mediated by dopamine release in the nucleus accumbens, and this reward reinforces drug-seeking behavior. So they've identified where the actual addictions are occurring. It's in the nucleus accumbens. The nucleus accumbens of the midbrain is where they have identified it. Now, as we break into the hindbrain, I don't particularly like their large words here, metencephalon and myelencephalon. In the metencephalon, we have the pons, okay? The pons and cerebellum. Well, the pons has two particular areas in it. We know from our lab test that the pons deals with regulation or rate of something, right? Particularly breathing. Well, here's your two respiratory centers that are in the pons. One's known as the apneustic center, and the other the pneumotaxic center. And really what we have is the apneustic center tells us what rhythm of breathing we're going to breathe 16 times a minute, okay? 15 times a minute, 14 times a minute. The apneustic center is telling us that. Now, if we're going to inhale 15 times a minute, we've got to have a system to tell us to exhale, right? So basically the pneumotaxic center says stop inhaling. So do you stop breathing? No, it's just in a rhythm. You stop inhaling, so you exhale. And then the pneumotaxic says inhale, and the apneustic center says inhale, pneumotaxic turnaround says exhale. So one says inhale, exhale, 14, 16 times a minute. The damage to the ventral pons can produce a rare condition called locked-in syndrome, characterized by paralysis of almost all voluntary muscles so that communication by the awake person is possible only by an eye blink. That's kind of unique, but I think we may have seen that on a movie at some point in life, where somebody communicates by an eye blink. Of course, the cerebellum, we know, deals with balance and coordination. The myelencephalon, the medulla, we know deals with vital centers, and they list vasomotor, cardiac control, respiratory, it's all there. And then we move to reticular activating system, and this is your, again, kind of back to your awake, alert type system. This plays a role in while you're sleeping to allow you to tune out things you're used to. If you're in a new place and there's a new noise, does it bother you? Does it keep you from going to sleep? I mean, if I'm sleeping in a motel along I-40, big trucks keep me awake all night. If I'm sleeping in a tent on Broken Bow Lake, crickets don't bother me a lick. I like crickets. I like whippoorwills. Those things, I mean, you could turn that recording on in my bedroom and I can sleep like a baby all night. Crickets bother some people. So this is what this system, how many of you have to sleep with a fan on? This is my classic question here, probably the largest majority of you do. If somebody come in and turn that fan off, would it affect you and your sleep at that point? It could possibly even wake you up. Anybody live near a railroad track? Used to? You got used to the train coming through. If you didn't, it's like first night you spent, the train comes through, it's like, it wakes you up. This system makes you used to your surroundings, things you're used to. It gets you used to those, so those doesn't bother you to getting in and getting through your sleep cycle. There is one thing that a mother will never get used to: the crying of their baby. That will always wake a mother, and it will be from a distance nobody else can hear. We'll try to put the kid on the other end of the house so we can sleep. Mom can hear it. It'll be coming through the walls somehow, some way. But Dad shuts them out day one. It doesn't bother us at all. But if Mom's not there, this is really unique though. If Mom's not there, Dad tends to sleep lighter, and I don't know why that is. It's almost like we've got a responsibility again. Maybe it is. Maybe it's a guilt trip we put on ourselves. Oh, man, if I let the kid die, well, the wife's gone. I'll never live this down, so I better take care of this kid. Geez, you call her 14 times. When are you coming home? You know, can't survive without her. 228, there's other neurons in the RAS located in the lateral hypothalamic area that tend to deal with narcolepsy. Narcolepsy affects about 1 in 2,000 people, and that's where you just, no matter what you're doing, you just fall asleep. I won't let these people drive because you can be cruising down the road, radio blaring, holding a conversation, and bam, you're asleep. It makes no sense, but that's some messed up stuff. There's some medication that helps control it, but it's not perfect by any means. Then let's look at spinal cord tracts here. Ascending tracts, just right beside it, right out there beside ascending tracts, just put sensory neurons. That's what ascending tracts are, sensory neurons. Descending tracts, motor neurons. We get on the 232, page 232. We have 31 pair of spinal nerves, 12 pair of cranial. 31 pair of spinal, 12 pair of cranial. And then in bold print, the dorsal root is composed of sensory fibers. The ventral root is composed of motor fibers. And we have not done a reflex arc in here, have we? Okay. The reflex arc consists of these things. I'm trying to squeeze this whole chapter in on this particular tape here. We have first a receptor, something to take in information. What's going to trigger it is a stimulus. Stimulus triggers a reflex arc, but it's not part of it. Okay, it starts it. You have a receptor, which sends it by way of sensory neuron to the association neurons, which sends it back by way of motor neurons to an effector. Effectors are muscles or glands. Something's got to respond to this initial stimulus. And a reflex happens faster than we can think about it. That's why they call it a reflex instead of muscle contraction. Muscles do contract in the process, but it happens by way of reflex. And it's nothing more than picking up a hot skillet, not knowing it's hot. You reach out here and you pick up the hot skillet, and about the time you get it picked up, your reflex says, "Ooh, that's too hot," and you drop it. Now that's a reflex that prevents you from totally scorching your whole hand. If we pick it up and have to think through the process, we think, "Oh my, this skillet's way hotter than I expected it to be. It is frying my hand. I must put it down. How much hand have you lost by the time you laid this down? Our processing, see? So it's not like our body knows ourselves better, and so we have to, don't worry about processing, get rid of it, and then we'll process, oh my, that was hot. How much hand did I burn after you've got rid of the skillet? See what I'm saying? Then if you know the skillet's hot, and it's been cooling down, so you check it. You always check it with the back of your hand. Why? Because if it's really hot and you grab it, so you're gonna reflex this way, you don't reflex this way. You reflex this way. So you check it with the back of the hand, oh, it's not too hot. And the pot holder's laying right there, but it's not too hot, right? So you just grab it, head over to the sink and get about halfway to the sink. Oh, this skillet's a little hotter than I thought it was, so because we still have mind over control, the reflex didn't make us drop it in the floor, but we did get it tossed into the sink, right? So that's kind of where we're at with the reflex. There is mind over matter at certain points, if you previously think about it. But if you're not thinking, just reach and grab a hot skillet, reflex takes control, and boop, there it is. Now you got a bigger mess than you had. Any questions? That finishes chapter 8. We'll start 9 Monday. I'm shooting for a test next Friday. That's what I'm looking for.